All right, I'll take it over. Well, thank you for hosting us, and thank you, Harpreet, for all the shout outs earlier about Perceptron and Isaac. I'm here, Akshat, on behalf of the Perceptron team. So a little bit about myself, and we'll talk more about what Perceptron's doing and what we've been up to. So before Perceptron, I'm one of the co-founders of the business. Was at Meta AI for a little bit more than 5 years, essentially spending my time in two divisions focused on Reality Lab, where I led a lot of the on-device AI efforts, and then Fair, where I was working a lot on multimodal pre-training. So the intention of this talk is to essentially go over what we're building at Perceptron and how we're building it. So the agenda here today is to talk about where we are, um, then what are we building, what's Perceptron, what's our thesis behind it, and then share essentially the core lessons we've learned in our journey in building these physical foundation models, and finally close out with how it connects to the larger physical AI ecosystem. Okay, so where are we today? And I think the important premise about why a problem like this is important. And I think the distinction to make here is essentially across where do foundation models stand today and where are they helpful. So essentially the split that we've identified here is that there's essentially two domains of AI being applied across the industry. There's digital and physical AI. So the current state of foundation models are essentially optimized for the digital world. And what you'll see is that all the frontier labs that are building a set of foundation models, LLMs, et cetera, being built, are all focused on knowledge intensive and reasoning intensive domains. You want to go after coding agents, math agents, biology, chemistry, and solving for new insights at essentially an unbounded cost. Like the value of these systems, they can go and take on problems that a human could. Uh, and you go and scale these systems up and you go and solve for these new challenges. You see everyone competing in IMO, the different Olympiads for CS and biology and chemistry as well. All keeping a push on this direction that these models need to think longer, reason longer, and tackle very complex tasks. The issue comes down to when they start working in the vision stack and where they start building there. Essentially, the current set of models that go after vision, video, audio, etc., all take the primitive of the language model base and extend it with vision. And this means that if you're trying to address any of these knowledge and reasoning intensive domains, and you want to go and solve with the vision aspect as input, or even in the output domain, you can go and do this, but it's all built with the primitives of the digital world. So for instance, current models are very optimized to take a picture of a screenshot of a website and then write all the code that you need for it. Or a video recording of a demonstration, or like a picture of a diagram for a math problem, and we'd be able to solve for this. The issue is that the physical world essentially introduces a new set of challenges. One, the domain of videos and images or audio that you interact with in the physical world is much different than what you see on the internet. The internet's often down selected from the world because there's a lot of saliency in the world. The internet's a lot more focused on entertainment for people, a lot more selection towards building in the digital domain. So there's a fundamental shift in the data distribution of this problem as well. With that, there are also two essentially unique challenges that come up for physical world problems that don't come up in digital world problems. One is the next set of capabilities. The next set of capabilities in the physical world often involve systems that can integrate and interact with others. What does structured reasoning look like for images? What does it mean to have access to tools in the physical world? What does movement in the physical world mean? How do you understand the basics of physics? All these kind of problems that you have to solve for to build a truly promptable interface for the physical world. And the second thing is that you can't arbitrarily spend on these models anymore. You aren't bounded at essentially what the input is or the modalities that you're dealing with. So a lot of the people that we talk to essentially have hours of video streams that are going on. And you might even buy a camera for $100 or so and just want to like have it turned on and feeding to an AI system throughout the time. And the solutions that are built for the physical world right now let you do that, but the current foundation models will cost you thousands of dollars if you want to do that, even with the cheapest ones. And so this cost and latency concern also in like the real-time case isn't just about efficiency anymore. It's also about unlocking new capabilities and markets that you just can't have access to right now because they're not economically feasible. And so the pinpoint of Perceptron here is that we've identified what the shortcomings of the existing stack are and are running with the hypothesis of what does it take to build a new solution for physical AI. The idea being that if you were to start from the ground up and build a foundation model stack from the ground up, how would you build it for the physical world? So concretely to summarize, our mission is that we want to build AI systems that can perceive in its environment, reason through complexity, and take action in the real world. So, to briefly go a little bit more into our progression, where we've come from and where we've been building. We left Fair in Q4 2024, I think around the November timeframe, to go and start focus on building out these models. So the first realization was that in order to build and iterate fastly on foundation models, you really need to make sure that the infra and the data is nailed down. Like that's the primitive to any kind of foundation model being built, or any kind of model really being built. And so a good part of our first almost year was focused on making sure we have the best in stack infrastructure, data pipelines, filter and curation pipelines as well, training pipelines, everything put into place, including synthetic data as well, to build this core piece of infra that would let us iterate on competing with the frontier, essentially. So with this foundation laid out and built, then came our first release, which is Isaac 0.1. We'll talk about these in a little bit more detail in a little bit. But Isaac 0.1 focused on if you focus on the right foundations, how do you build in basic image understanding and structured reasoning capabilities that you need for the physical world. Isaac 0.2, which was our release back in December, took this a step further and essentially allowed us to look into what other LM primitives are. We went into reasoning and tool use and what does that mean to do in physical world in multimodality. Isaac 0.3, which is a little bit of a teaser, it should be coming out within the next month or so. So we'll share some sneak peeks of that. But essentially is getting into the early primitives of how that extends into video and robotic control. And Isaac 0.4 is our next directions around pushing on more modalities, improving latency in real time, and really scaling up what these systems are to build this true foundation of physical foundation models. So just to summarize what we mean by the frontier of perception. I think normally if you're looking at the frontier and building at the frontier for physical world problems compared to digital world problems, other problems that we see, frontier tends to be purely about quality. But the issue now is that there's also this price axis that isn't just about reducing costs, it's about unlocking those new markets we were talking about earlier. We need to build something that's at this intersection. So no longer is something at the top here, the frontier, you have to be top and to the left of what that is. And so this is essentially where we've been building, is that we want to get that performance that you get at a frontier model down to the cost you need to have something running always on and essentially be able to always observe something in the sense of perception. So our zero point 0.2 model currently is set out to achieve the efficient frontier of image, and that's essentially these two models right now. So Isaac 0.2 improves upon all the other open source VLMs that are out there at the 2 billion parameter mark. So they're designed to be quite small and quite efficient. And also, we made big strides between our zero point 0.1 model, which is the other black model on this chart here, to an even smaller model, about half the size in the 1B sense. So each of our generations keep improving upon the prior, not only in adding on new capabilities and performance, but bringing the same capabilities in the prior generation at a much cheaper cost. And we keep pushing these things forward. So this is just a breakdown of the different performance and benchmarks that we have. Everything in here is open source. It's on our website and such, so I won't spend too much time going into it. But essentially a breakdown of different capabilities and how we stack up compared to the other models that are very strong in the multimodal domain. Okay, so now for the crux of what I'm hoping to talk about is essentially when building these physical foundation models, what are the things that you really need to do and what are the things that we've learned along the way? And there's essentially four lessons that have come up in how we build our models. Actually many more, but I'll only talk about these four. So the first lesson we took is when we were building out our first model, Isaac zero point 0.1, and that's to focus on the foundation. So Isaac zero point 0.1 is a 2 billion parameter model. And a key theme behind our design of zero point 0.1 is to focus on a simple and efficient recipe that scales. So the issue is that today, if you look at building a VLM, specifically an image VLM that we're looking at for zero point 0.1 here, the issue was that majority of recipes have very complex stages involved. There's multiple rounds of pre-training, there's pre-training, mid-training, post-training. There's different modules that are being updated in different mechanisms at different times. The learning rates are all different for things that are going on. A lot of these hacks were done to get vision and text to interact correctly. Uh, And these systems end up working, and you end up getting reasonable models and such out of it. But the issue is that for building something stable, a foundation that you can keep building on top of, you want the simplest kernel of work. You want something that essentially your team can take and extrapolate on top of even further and further. And that's how you accomplish modality scaling, reasoning, and a lot of the other advances we talk about. So a big focus was what's the simplest thing we could build that sets this foundation, that gets to frontier performance um, through a single stage of training that lets our team iterate fastly. And it turns out that this is easier said than done. And a lot of work goes into the right data curation, the right infrastructure being done, the right speed that you can train on, which relates to your GPU costs, making sure your MFU stays high. All of this matters to be able to build that simple and efficient recipe for scale. And we accomplished in zero point 0.1. The paper talks about it in more detail, but zero point 0.1 essentially built a single stage of training that allows for full updates to the model. So no specialized learning rates per module, not multiple rounds of training. You can come up with one recipe and train that, and you can achieve frontier performance at the 2 billion parameter scale. So this was something that was quite impressive to us because other models, like even the Gemini Flash series, we started to compete with at something that was like runnable on a cell phone. The second part about building a foundation is that you wanted to represent essentially what customers want. And also, you want to impose the least restrictions on your model as possible. So this came down to the principle for us of natively representing every input. So the idea here is that when you deal with the VLM models at that time, I think now there's a larger mix here, but at that time, largely things were fixed to a single resolution. So the issue is that if I'm doing some complex OCR task of a full like IRS form and I want to pull out all the checkboxes and all the text versus I'm trying to classify an image, the resolution I need to deal with these two problems is inherently different. So forcing a fixed resolution or even a bucket of resolutions essentially becomes a shortcoming of a foundation model if we're to take this on. So a big focus we had is that how do you persist this resolution? You can pass in higher resolutions to our model and trade off tokens for it, lower resolution, and it'll be faster to run too. That's left to the user to decide how they want to make the quality and latency trade-off, essentially. And the technical challenge comes here that when you want to run larger jobs, training jobs, inference jobs, etc., how do you do this while maintaining essentially no padding? If you have any padding during a training system or inference system, that's essentially wasted compute. So you want to get rid of this as much as possible, and how do you pack it all together? And the final thing here is that not only do you want to have a VLM that performs at the frontier and competes with all the other VLMs that are out there, you also need the capabilities that are required for physical world systems. So a big issue here was that if you go and ask a lot of the VLMs now, like, oh, in this screenshot of my screen right now, where's Jimmy in the call? And it's going to be like, oh, Jimmy's underneath the presenter Akshat, but above the three other presenters that are in here, and then talk about that. But if you're building any kind of system that's very difficult to interact with, that's not enough information to integrate anywhere. It's tough to reason over. It's tough for a human to even judge correctness on. This becomes very difficult because we're forcing these VLMs into reasoning and text space. So one of the big things that we did is that we enabled our model with this new capability called visual citations. I think Harpreet actually showed off a lot of this work earlier, but the underlying thing here is that whenever you talk about something, you should be able to visually cite it. So the examples on like the cooking scene in the kitchen on the left-hand side of when recipes are being talked about and ingredients are being discussed, you localize where they are. And we found that this improves from a model quality perspective because you're grounding everything you talk about, reduces hallucination, but also from a user perspective or a downstream application of this model, it's quite helpful because often you want the bounding boxes or the segmentation masks or points to what you're talking about. You might want integration into other systems, in which case this visual structure is actually quite helpful because now you can pass the information along to some other part of your agentic pipeline. And it's also helpful for human review. Like a human can go back and look at this very quickly, and I can look at the right-hand side where there's it's an assessment of whether a person's wearing the right PPE, and I can see, oh, this is exactly what the model's talking about. It did identify the shoes, but look, they're not wearing gloves because the model didn't talk about that. So there's a lot more interpretability that I get out of this as well, working with these models. So 0.1 was focused on, yeah, or lesson one was focused on building the foundation. Lesson two is essentially on how do you extend into visual primitives. So the idea here is that the LLM community, if you take away vision, has been progressing forward, and there's a ton of advances that have come up primarily in two domains in test-time compute. One is text-based reasoning and being able to think through answers before you respond to them, and the second is through tool use, and that gives your model some ability to change the context it's interacting with. The issue is that the current recipes, if you go and build them out for VLMs, VLAs, or any of the multimodal applications, is they fall short on multimodality. Essentially, you want a reasoning mechanism that lets you reason directly over pixels and talk about them, ground through them, and iterate about the image. Where a lot of the reasoning methods today will essentially focus a ton on text reasoning, and they aren't designed to go and interact a lot with an image. And I think this is further exemplified through this idea of native tool use. So native tool use is also essentially an instantiation of reasoning, is something we enabled in Isaac 0.2. But essentially it gives our models the ability for primitives within the visual domain that let it adjust itself to perform better on a different task. So it's vague, but I'll give you an example here. Essentially, our model has this ability to focus. So what we saw is that if we were getting our human annotators to work and interact on a few different things, the idea was that like if you gave them a satellite image and asked them to find like different trees or different houses on that image, the human themselves would start to zoom into regions. And it's because you're bombarded with information that is very difficult to reason over every piece of detail if you take everything at the face value. You have some ability if you want to focus on a region, you want to zoom into it. So a lot of our investment to 0.2 also went into what happens if you gave our model the native ability to zoom into this. So functionally, what this looks like is that when the model is reasoning over some image, it can actually zoom into a region and it can allocate more compute to that region. And we found this to be very helpful in getting fine details correct. So like here's one example of what this reasoning and tool use looks like. So again, that same case of like there's a person you want to identify what PP gear they're wearing, and we ask them questions, you can see that the model, when enabled to reason and tool use, is able to actually zoom into the different regions, understand them better, and present a summary of the different things that are going on. Actually, a minor point here, but an important one. A big focus for us is that everything is within one model. So a lot of the existing models today, essentially, you have a thinking version, a non-thinking version, a tool use version, a non-tool use version. We essentially have one model that supports everything. You just enable the different things that you're looking for here. So here's a bit more of a visual example. Like in this image right now, you want to go and look for like where's the phone number? And I don't know if you can see it or not, but it's actually quite difficult to see. So the model starts to take actions to zoom into the image, and you'll see that eventually it lands on being able to read the exact phone number that was presented on the screen. Another example of where information just isn't present at a first glance that zooming essentially enables you to do. So 0.2 was a step towards how do you build extend these primitives to work well in the visual domain and solve for these problems. There's also the equivalent of being able to reason over the image as well. I think this aligns more with what people have seen if you look at like the Claude thinking mode or GPT-5 thinking mode. We can enable the same thing directly for images and reason about them. The impressive thing here is that it's all done at the 2 billion parameter scale. So, okay, that talks about what we've released so far and where we've been going. Now I want to talk a little bit more about where we're headed. And the idea is that we've built this kernel of like these primitives of language models that have been shown to work in the digital domain. We've been able to build out this like the reasoning, the tool use, the foundation of being able to build a strong VLM. And this is the kernel of work we're using to expand across modalities and essentially continue to rebuild the stack. To share a little bit more of intuition here, essentially what you're seeing right now is our image models. This is Isaac 0.1 and 0.2. A single frame, like shown on the left-hand side here, and producing some text and reasoning and interacting about that single image is what these image models have essentially set out to solve. The next step for us and what we're actively working on, and we'll talk a little bit more on how this is possible, is to expand beyond images to video. And all that video is essentially is a frame of images. There's of course more to understanding a video than just doing like length extension on top of an image because there's an like axis of actions and temporal natures of like different events that are going on that you want to be able to understand. But functionally, the image models are being used to bootstrap the video models because the underlying unit of a video is still a frame of an image. So you can build a lot of the stuff around whether it's synthetic data, rejection sampling, different kinds of stuff on the RL loop, or even the training side, all can be built in using our image model as a core starting point to bootstrap these video models. And we've seen a ton of success in being able to build to that, and how we go and accomplish a lot of things here, including like dealing with long context issues. So that's how you go from essentially image, which is a single visual asset, into a series of visual assets along with text accompanying them. And if you can do this, and essentially what we've done, then action falls into the same thing. And this is one of the next big frontiers we're taking on as well. Uh, that once you have models that can reason temporally and understand where things have been going and how to and what's going on across like a video, for instance, you can extend that to be reasoning over and inferring how actions I take can influence what happens. So now we have a video which has some actions involved interleaved within it. And those actions are essentially control sequences you can send to a robot. And so you can model these details, and on like robotics falls into this, even things like desktop use fall into this, that there's this concept of a trajectory, which is now that there's a single frame, there's a state along with it, and then action along with it, and expanding across the temporal domain and understanding how those actions influence the rest of your trajectory is a problem that a VLA is designed to solve. So the purpose of this here was to show that if you build the right foundation and the right starting point that's designed to be simple and efficient, everything else essentially falls into place and follows from that, including going into video and action, which is the direction that we're headed in. So, okay, that's easier said than done. We want to go and expand into video and action. So a couple more lessons we're learning along the way, and this is some of our most recent work that will either publish recently or is going to be published tomorrow. So you can dive into this a bit further to understand where we're coming from. But the third lesson in building these physical foundation models and generally multimodal systems itself is multimodal data is multidimensional. So what I mean by this is that of course, there's many dimensions to data, but if you look at each data point individually, and if you start collecting a ton of data to go after different multimodal capabilities across any of the modalities that you're interested in, what you find is that there's essentially this atomic units of capabilities. So there might be something like visual question answering, OCR and character recognition, knowledge intensive stuff, structured reasoning, pointing to objects, localization, temporal reasoning. There's a set of these capabilities that exist within a data point. And it's important to be able to tease apart your data set into the dimensions that are these different capabilities. So the key thing here is that like you might end up with a sample that's like what's the I mean on this what's the largest number on the screen? And that has like an OCR capability in here. There's some aspect about reasoning spatially to localize the different things that are going on. You can tease apart each data sample across the different capabilities. And so our here realization was that if you spend some time to go and do this, your data samples end up actually being very multidimensional. That like they have spikes in like certain capabilities compared to others. And it's important that you understand this multidimensional aspect of your data or these capability breakdowns of your data set in order to effectively curate the right data to train your models and the right recipes to enhance your capabilities within your foundation model. So with that is our paper that's coming out, I think tonight, tomorrow, called Skill Rater. And the idea here is that you should be able to take exemplars of these individual capabilities and train models that essentially can go back and rate data for you. And they'll essentially give you like a score on how well they're aligned to that capability. And what you can do, and the way you build this is through this meta learning objective that you see how training on the sample influences your loss on these different domains that you care about. But if you go and you build towards this and you start building these models that essentially give you capabilities to rate data in these different domains, you can start building a graphic like the one earlier. Like you can understand the multidimensionality of your data across these capabilities and then break down your data set this way. And what we found is that once you do this and you score your data sets, there's essentially a natural curriculum that comes out of training. That instead of training on your entire data set, you should early on focus on training on essentially everything. I think aligned with most people find. But as you progress, start taking the top quality data from each of these domains. So take the top 70% of your VQA data, your OCR data, and your knowledge intensive data. then take the top 50, 40, 30, 20, 10, etc. So you keep narrowing the funnel to focus on higher and higher quality data within those domains. And this way, you essentially have a curriculum that lets you learn across your entire data set. Because if you only focus on the high quality subset, you'd essentially end up with too few samples to learn more generally. Uh, it lets you follow this natural progression of training that gets you from the general capabilities you might need for diversity to high quality refinement you need for your end tasks and users. So a quick TLDR on this is that it ends up working out quite well. If you build an approach like this and deploy it, and you retrain models on like large mixes of data, you get pretty consistent wins across the board. Uh, which essentially is a proof point that your data is something you really need to understand, and capabilities are a very important breakdown to have, and use that in essentially weighting and curating your data. The last lesson I'll share here, and this speaks to also some of the work that we've been doing at FAIR before we started Perceptron, is this fundamental nature of text architectures just don't scale multimodally. So we had this work back in 2024 called MoMA, which essentially studied mixture of experts and mixture of depth models, and essentially applied them to omni-model settings. So models that can take input across all modalities and output across all modalities. And the realization was that the text community was starting to build out these mixture of expert models. We were running the same experiments, we were realizing wins, but it came down to this shortcoming that everyone was treating text and image the same. Like a patch of text and a patch, sorry, like a word of text and a patch of pixels were given the same amount of compute in these models. They were treated the same way and they were mixed and fused together. And this ends up being a shortcoming that you don't have the same essentially form of data. You can't have the same form model. So our work on MoMA essentially showed that if you break apart within your model, like still have one model, but have maybe a group of text experts, a group of multimodal experts or image experts, and scale them independently, like you might have fewer text experts and image experts, or vice versa, depending on your target domains, you can actually, with the same compute budget, realize significantly stronger models. So this essentially gave a proof point to us that there's something inherent about multimodal models that's different than text models, and you can't be treating them the same as you would with text architectures. And once you cross this threshold and start designing for multimodal directly, you can start getting significantly more compute controlled ones. So this comes into our most recent work, which we published earlier this year on sparse architectures. Is essentially the alternate framing to what I was saying earlier is that there's two forms of sparsity that you need in mixture of expert style models, which is a core architectural innovation that we've been focused on. One is you have weight sparsity. So if you know a mixture of experts, essentially this is where all mixture of experts fall into, is that every token is given a set of experts to choose from, and you fragment your model across a series of experts. So if I have 10 tokens, each of them selects like two experts, and I have eight experts total. Now instead of a few experts getting all my tokens, many experts get some tokens, and I can build in some specialization to the model. And this is the predominant way that most frontier labs are scaling up mixture of experts right now. The alternate that Momo was poking at, and some of the other recipes we're poking at, and what we were focused on, is around data sparsity. The idea here is separate. It's that rather than thinking about it from a model perspective and a weight perspective, that there's a capacity that every expert has and how many tokens it could take on, let's do it the other way. It's that, or sorry, the other way around. Rather than having it that a token has a capacity of certain experts it can take on, we swap it the other way. An expert now has a capacity of how many tokens it can take on. And what this essentially lets you do is that it lets you form essentially this dynamicness within the data itself. So each token can now decide how many experts it wants to use. Um, so because this is happening, you can have some tokens that get skipped, some that get a lot more computes, some that get like a medium amount of compute, and you essentially can bake in this dynamicness to your model. And this essentially builds on this idea that there's inherent sparsity of information. Like if you look at the information that's in a text token, it's super dense. There's a lot of meaning behind a word. But if you look at the patches of pixels within a video that make up a single token, that's super sparse. A lot of it's really repetitive across the video. A lot of the information is actually spread throughout that video. So dedicating the same amount of compute to a text token as you would a set of pixel patches doesn't seem to be the optimal approach. And we actually prove it isn't. So if you look at the recipes here and the models here, essentially the blue points here show your standard mixture of experts model, essentially ones that aren't data sparse at all. We showed that if you add this data sparsity dimension to it, you essentially can significantly improve your performance. Like you can see training loss here on the left, where lower is better, and eval performance on the right, where higher is better. That at the same compute controlled, like same performance that you have, you can get significantly better models by having data sparsity in your recipe. So it's a clean win you can add on to any multimodal training, a mixture of experts models. The last point here is that it's actually quite interpretable what these models are doing. So what do these models actually learn to do? It's essentially they can change the compute they allocate per token. So to take an example of this chart on the right-hand side here. Um, Essentially, on the left-hand side is the actual chart. The right-hand side is the compute map. The darker the color, or the redder the color, the more compute's being spent on that token, and the bluer the color, the less compute's being spent on it. So dark blue means that essentially no compute's being spent. And you can essentially see that the model decides to focus its compute on the edges of this line, which appear to be the most important, along with more compute also on the text labels and the axes of this line, which is something you'd expect as a human. Like, why spend compute on the background patches? Like, the equivalent of a normal mixture of experts or dense model would be that everything is red here. So rather than having any compute being spent on the background patches or equal compute being spent, we're reallocating that budget to be spent on the details that matter. And you can see that this changes based off the condition of your question too. So like a fruit stands here, and you might see something very generic, like answer my next question based on the image, in which case the model kind of focuses across everything. It's more distributed across the full image. Whereas if you say segment out the fruit, you can see that the model's starting to already focus its compute on where the fruit is in the image. So again, these are the primitives that you need for have this essentially model the sparsity that you need for multimodal models. And the last point I'll make here is that essentially those are the lessons on how we build models. There's also lessons on how you need to integrate with the physical AI ecosystem. And this is where we're looking to collaborate with as many folks as possible, and we'd love to chat with more folks where we can. Essentially, the realization we've had on our product and commercial side is that the needs are broad. There's a set of folks that want to interact directly with the OpenAI compatible APIs, integrate directly into their system. The more power user that just knows what they want to do and integrate their tech directly, and that's where we offer directly our API service. There's a second set of users that essentially have ideas of what they want to build, but they want to iterate on top of. And the truth is that forming multimodal prompts is quite difficult. There's an intuition that folks have, and they've built in text prompting that just hasn't transferred to multimodal yet. So to do this, we've released essentially our Perceptron SDK, which lets you interact with primitives in the visual domain. So essentially on the right-hand side here is an example of how you do that, is that you can write Python code on how you reason over an image, a text, do in-context learning, what kind of output formats you expect. We let you configure that and write these more like in a custom DSL, what your task looks like. And the last point is that there's no one size fits all solution. There's many people that want to deploy directly on their hardware, want to run within their systems, build more complex agents and systems around it where they want access to the raw model and the capabilities. And this is where we're pushing a lot on open source integrations. So as you know, we're with Voxel 51 now. You can interact with the models directly in there. We released our models on Hugging Face and on VLM. So we have very high performance throughputs that are throughput engines that are being served to the community right now. You can go and you can integrate these models wherever you want and build from it.